Section 11.8 is all about multiplying and dividing our radical expressions. We just did addition and subtraction, and it was important that they were like terms. With multiplication and division, that doesn't matter. We can multiply and divide radical expressions using the product and quotient rules that we learned 2 lessons ago. Always try to simplify when you can. So some of the stuff we've done just by virtue of the product and quotient rules, so let's just refresh our memory. Like the very first problem, A, we've done a couple of examples like A, where we've kind of gone backwards from this. We might have taken something and split it up. But when I look at this, I don't know the square root of either of those, so I can simplify them and then combine them again. Or I could combine them first. 8 times 6, since they're both underneath the square root, I can multiply them together, and I end up with the square root of 48. Still not simplified, so we have to break it down. You could do a factor tree or look for the biggest perfect square. This is one that we've done a couple times already, and I know that 16 is the biggest perfect square that goes into it, and it goes in 3 times. So I take the square root of 16 and I get 4. And then 3 is stuck inside. So all of this, square root of 8 times square root of 6, simplifies to the square root of 4 times the square root of 3. So now the next one. Remember, a square means that you have 2 of the same thing. So I have 2 root 5 times 2 root 5. The rule with radicals is that you can only multiply things that are on the outside with other things on the outside, and you can only multiply things on the inside with other things on the inside. So that means that I can do 2 times 2, which will give me 4, and then the square root of 5 times the square root of 5, which is the square root of 25. And then that can obviously be simplified to 4 times 5, or 20. We could also get this by kind of distributing the square. This only works if it's multiplication. 2 squared gave us that 4, and the square root of 5 squared gave us 5. Multiply them together, we get 20. This one has some variables in it, but because 3y and 12 are both underneath the square root, we can combine them to give me 36y squared. Y times y is y squared. And then, luckily, both of these are perfect squares. We can split this up into square root of 36 times the square root of y squared. And we end up with 6y. Now, the awesome thing about multiplication and division, we've already discovered, is that I don't know the square root of 3y, and I don't know the square root of 12y. But if I'm multiplying them together, I can simplify them, take the square root, and get a nice, pretty answer out that I couldn't have gotten before. So now let's use the distributive property. We're going to be doing distributive property and then double distribution like we did way back in the day. And then we got to get to something called rationalizing the denominator. But these rules are exactly the same as rules that we've used without radicals. So if I want to distribute the square root of 3 to 7, we do not end up with the square root of 21 because 7 is on the outside and 3 is on the inside. All we can do is write it 7 root 3. It'd be like if I had x times 7. You couldn't turn it into something different. It would just be 7 times that x. And then I have the square root of 3 times the square root of negative 8. So since both of these guys are underneath the square root, I can actually multiply the numbers together. 3 times 8 is going to give me 24. Now before I box this up and say we're done, we need to double check that we can't combine what we have and we can't simplify what we have. So 7 root 3 can't be simplified, but 24 can. And you can go about this a bunch of different ways. You could look for the biggest perfect square that goes into it, or you could break it up into all the factors. 4 is the biggest perfect square. So if I take the square root of 4, I end up with 2 on the outside, and 6 can't be broken up anymore, so he stays on the inside. Now that they're both simplified, again, double check that you can't combine anything. And in this case, they're not like radicals, so we have to leave them separate. Try B on your own, and then check my answer when you restart the video. Hopefully you ended up with a nice, pretty 10. I can't simplify the square root of 2, I don't know the square root of 8, or the square root of 18. But if I multiply them together and then add my product, I end up with one integer. No more radicals. So now let's try some double distribution. The rules are the same as they were before. I need to take each of these things, the 3 and the negative root 8, and multiply them by both terms in the other parenthesis. So 3 times 2 is going to give me 6. And then 3 times root 8 gives me 3 root 8. And now I have to do the same thing with negative square root of 8. If I multiply that by 2, it gives me negative 2 root 8. And then negative root 8 times positive root 8 gives me negative root 64. And then some simplifying needs to happen. So the 6 right now can't be combined with anything. These two are like terms. So I have 6 plus the square root of 8. There's just one of them left. And then the square root of 64 is a number I know. It's just 8. So more simplifying can be done. I can combine 6 and negative 8 to give me negative 2 plus the square root of 8. And we are still not finished. The square root of 8 can be simplified. You will do the square root of 8 a lot. You should know that the square root of 8 is always, you can take a group of 2's out and 1 2 is left in there. Square root of 8 is the same thing as 2 root 2. So negative 2 plus 2 root 2. Now there's lots of 2's in here, so don't be tempted to add together this negative 2 plus 2 here. Negative 2 doesn't have a root 2 on it, so they're not like terms and you can't combine them. For part B, we cannot distribute. This does not work. It only works for multiplication. So this one here, multiplication. With addition, we cannot just distribute its parts. What this is telling us is that you have 2 of these things. I have 4 plus root 3 times another 4 plus root 3. So give this one a try on your own. Make sure that you can double distribute correctly and simplify correctly. Pause the video and then check your answer with mine. I ended up simplifying all of my numbers down to 19. And then I had 4 root 3's twice, so I have 8 root 3's. Nothing can be simplified, nothing else can be combined, so I'm done. Now let's get into this thing called rationalizing the denominator. If you remembered from an earlier video, we're not allowed to have square roots in the denominator. Weird rule, but it's a law of simplification. If you have a square root in the denominator, that means that it's not simplified as much as it can be. So if we take a look at A, I don't know the square root of 11, and it can't be simplified. I don't know the square root of 3, and that can't be simplified. And even if I combine them into the square root of 11 over 3, I still can't simplify it, and I still can't do anything with it. So, no point in doing that. Instead, what we're going to do is something called rationalizing the denominator. And a rational number is one that does not have a square root. So when we say rationalize the denominator, we're saying get rid of the square root, give me just a nice, pretty number. So in order to do that, I want this fraction to maintain its original value. And in order to maintain its original value, I can't change the top and the bottom separately. I have to change them together. So think about with a fraction. If I told you a fraction 7/10, and I wanted an equivalent fraction or a fraction that meant exactly the same thing as 7/10, I could multiply the top by 2. That'd give me 14 in this fraction. And then what would the denominator have to be to make it equal? Well, I'd have to multiply the bottom by 2 also. 14/20 and 7/10 are exactly the same amount. what we did here is multiply by 1. 2 over 2 is the same thing as 1, so we didn't change the value of the number, we just changed the way that the number looked. We're going to do that with radicals. In order to undo a radical, hopefully you noticed in this problem and in the problem before it, that when I do the square root of 3 times the square root of 3, I end up with just 3. You end up with just a number, not a square root, because you basically have the square root of 9 is really like the square root of 3 squared. And we know squares and square roots undo each other. So in order to undo square root of 3 here, I'm going to multiply the top and bottom of this fraction by the square root of 3. And if we multiply the top and the bottom by the exact same thing, we're really just multiplying by 1. So we're not changing the value of the number, we're just changing the way the number looks. So on the top, I'd end up with the square root of 33, and on the bottom, I get the square root of 9. Square root of 33 can't be simplified, and it can't be broken down, but the square root of 9 can. So I end up with the square root of 33 over 3. Be very careful not to get the square root of 11 from here. The square root of 33 and then divided by 3 can't be simplified. So this is my answer. Square root of 11 over the square root of 3 is exactly the same thing as what we got here. If you were to type both of them in your calculator, you would get identical decimals that went on forever and ever. So now it's simplified because there are no radicals in the denominator. So B, we can approach a bunch of different ways. We could simplify the square root of 20 first, or we could just get rid of the denominator. I'm going to do it both ways, and then you guys can pick whatever way works best for you. So I know I have to do this rationalizing the denominator because I can't simplify the top or the bottom together. Like 13 over 20 doesn't simplify to anything. So I have a square root in the bottom. Even if I simplify the square root of 20, I would end up with 2 root 5 in the denominator, and there's still a square root down there. So I need to get rid of that. Now I'll go back up to this, and we're going to do the same thing. I just want to get rid of the square root. I don't really care that that 2 is there. We're allowed to have 2's in the denominator, but we're not allowed to have the square root of 5 in the denominator. So what I'm going to do is multiply the top and the bottom by the square root of 5. And if you multiply the top, you end up with the square root of 65m, all divided by 2 times the square root of 25. Square root of 25 is 5, and 2 times 5 will give us 10. Now this is the answer. Nothing else can be simplified. We can't break down that 65. We can't take out an m because there's only one of them. And we can't do anything with the 10. Now this would work exactly the same way if instead of writing this as 2 root 5, we just took this 13m over the square root of 20 and tried to get rid of the square root of 20. So we can multiply both the top and the bottom by the square root of 20. If you notice our numbers are going to be a little bigger here, we're going to have the square root of 260 m's on the top, and then divided by the square root of 400. Whoa. Now I know the square root of 100 is just 20, and then we have to simplify the top. So 260, ironically the largest square root that goes into it is just 4. And 4 will go into it 5 times 13 times, which is 65. Yeah, 65 can be broken up into 5 and 13, but there's no more pairs of things and no more perfect squares. So if we take the square root of 4, we get 2. And then we're left with 65m on the inside. And now we have this 2 divided by 20 that we need to simplify. And 2/20ths is the same thing as 1 over 10. So we still end up with the square root of 65m all divided by 10. It really doesn't matter which way you do it. I personally like the first way better, to simplify it first so that your numbers are a little smaller. But if you forget to simplify it, or it's not as obvious to simplify it, you can always rationalize the denominator first and then simplify whatever you have left over. So rationalizing the denominator when it has a sum or a difference is very different. Back here, when we had a product, this 2 times root 5, if I multiplied it by 2 times the square root of 25, I'd still get just a plain old number, that number 10. But this time, if I were to take this fraction, 1 over the square root of 5 plus 3, and multiply the top and the bottom by just the radical, think about what would happen in the denominator. I'd get the square root of 5 on the top, multiply these two guys together, and I would get 5. But when we multiplied these guys together, I would get 3 root 5. I would still have a square root in there. And it would become this vicious cycle of over and over just one of them having a square root. So we need to do something called multiply by its conjugate. And a conjugate is something that follows this property right here. Conjugates are matching sums or differences that take advantage of the difference of squares property. So let's think about this if we just had letters like A and B. If you multiply A times A together, you end up with A squared. A times negative B, you get negative AB. B times A, you get positive AB. And then finally, B times negative B gives me negative B squared. What's going to happen every single time if your A's and B's are the same and they have different signs is your middle terms are always going to cross off, no matter what. And then you're going to end up squaring your first term and squaring your second term. Now, if these had square roots in them, the squaring part would take care of the square root. So you will always end up with rational numbers if you multiply by the conjugate. So if we look back up here, the conjugate that I would want to multiply the top and bottom by looks almost identical, has a square root of 5 and it has a 3, but we want their signs to be opposite because we want this middle term cross off to happen. And remember, whatever you multiply on the bottom, you have to do exactly the same thing to the top. This one, square root of 8 over or minus the square root of 2 in the denominator, we could multiply by something almost identical. We want the square root of 8, and we want the square root of 2, but we want them to be adding. And whatever you do to the bottom, you have to do to the top. So let's do some problems like this rather than just talking about them. So here is the first one, 1 over the square root of 5 plus 3. So we've already talked about what we need to multiply it by. I want to multiply it by the square root of 5 minus 3, and then that same thing on the top. Awesome for us, we're just multiplying it by 1 on the top. What we are really doing here is distributing whatever this number is. 1 times the square root of 5 is just the square root of 5. And then 1 times negative 3 is negative 3. Now on the bottom there's a little more work involved because we need to double distribute. The square root of 5 times the square root of 5 is going to give us the square root of 25. Square root of 5 times negative 3 is going to give me negative 3 root 5. And now here's the part where we can check to make sure that our conjugate worked. If I do 3 times root 5, I'm going to end up with opposites that should cross off. And then 3 times negative 3 gives us a negative 9. then, yes, these terms are exactly the same but opposites, so they cross off. 25 is really just 5. So on the bottom we end up with 5 minus 9. So that gives us a nice, pretty negative 4 on the bottom. Just a plain old number. No more radicals, which is what we want. And then we have the square root of 5 on top, minus 3. Double check that nothing else can be simplified, and in this case it can't. So we're done. Now I know this concept is kind of difficult, but I want you guys to give this next one a try on your own. Go ahead and pause the video and then you can check my answer. So we did all of that work to end up with 1. As weird as that sounds, we can kind of check this one to make sure that what we did was correct. And it only works for this problem, but just figured I would show you this in case some of your brains were thinking this. Square root of 8, hopefully it is drilled into your brain that the square root of 8 is really 2 root 2. So if we go back to this, I could really write the denominator as, good Lord, could really write the denominator as 2 root 2 minus root 2. So this is really like 2 root 2's minus 1 root 2. So I just end up with 1 root 2 on the bottom, and square root of 2 divided by square root of 2 will give us 1 also. So just a coincidence that we could have simplified that problem, but you need to know how to rationalize the denominator because, like the one we did before, not everything can be simplified first. If you have any questions, make sure you mark it, and we will talk about it in class tomorrow.